Hi, welcome to Engineering Mechanics. My name is Arun Srinivasa and I'm faculty at Texas A&M University. Today I'm going to talk to you about how do you do dynamics of systems in a fairly simple way. We are not going to do any advanced things. This is the basic stuff. So we're going to tell you how to think about systems and figure out what to do, okay? And how to use the appropriate coordinate system depending upon the situation. Okay, let's get started. So first item is a decision tree. See, the thing is, when you're doing problems in a class, you always know whether it's statics or dynamics because it comes in a particular section. But in real life, you don't get objects where things are labeled. This is statics, this is dynamics, this is what you're supposed to do. You have to figure it out. So let's look at a setup and see if you can have a rough idea of how to figure this out. So you start out by looking at what's your idealized situation. You have simplified it already, you have drawn a nice free body diagram, this, that and the other. Your first level of decision is that, is this a slow moving object or stationary object, or is it a fast moving object? If it is a slow moving object, then you have to decide whether it is completely stationary or it's a slow moving mechanism. If it's completely stationary, it's called a structure. So then you have to figure out, well, can I treat it like a truss or should I treat it like a group of rigid bodies? Okay. If it is a truss, then your favorite choice is method of joints. That's the easiest one to do and you know how to do it. If it's rigid bodies, you do summation of forces, summation of, you draw a bunch of free body diagrams and do summation of forces and moments. So if you start out with the idealized situation and you find out you're going to use statics, you have to decide whether it's a structure or a mechanism. If it's a mechanism, you have to ask yourself, how important is dry friction to this mechanism? If dry friction is important, you go back and you treat it exactly the same way as you treat with rigid bodies. If dry friction is not important, then you can do the principle of minimum potential energy, which is a very clever way of getting things done. Okay, so this is on the static side. On the dynamic side, you have to figure out whether it's a kind of a free moving body like cars and things like that, which are really going very far, or is it more like a mechanism? Is it a fast moving mechanism or is it a fast free moving object? If it's a free moving object, you probably want to use a specialized coordinate system, like the two coordinate systems we are going to talk about are path coordinates and polar coordinates. And if it's a mechanism, then you have to do like what you did for a mechanism here, which is choose the appropriate kinematical parameters, and then you have to find position vector and velocity vector. And it will turn out you have to do a whole bunch of differentiation, and then you have to do summation of all forces equal to mass times acceleration, summation of moments equal to inertia times angular acceleration. So this is your decision matrix, and you need to memorize this because this is how you have to think about your systems. Okay. And then if none of these things are simple, then you better take a grad class on Lagrangian mechanics, which will teach you how to do fast moving mechanisms by a variation of principle of minimum potential energy. So this, if you think it's a plug for Lagrangian mechanics, yes it is. It's a beautiful thing setup. Okay, very good. So now that we have a decision tree, let's look at our first example of this one. We've already beaten all these things to death. We have to really look at this case, and we'll look at a little bit of this case. If you go to the next class, which is the vibrations class and dynamics class, you will see much more about mechanisms. So we're going to look at the next case, which is path coordinates. So when do you want to use it? When you know the exact path. So the road should be known. So here you have the road and the road is known, and this is a path coordinate system. How does it work? Coordinate so pick a datum. Let's say I start with here, and the coordinate is actually how far have you gone along this road to the point of interest. That's the point of interest, and that distance is S from here to there, and this is a function of time. So this is my kinematical parameter. Everything will be written in terms of this because path is known. It's a beautifully simple setup. Why is this useful? because you don't have to sit there. If you looked at the previous cases, you have to do differentiation, but for this particular setup you get canned expressions for velocity and acceleration. You don't have to sit there and differentiate. The differentiated expressions are given to you. You just have to identify, plug and chug. So this is a very nice setup. So let's see how that works. And also, by the way, it's physically very intuitive. So how to use path coordinates. So here is the object. Here is the car that's going around on a road, and it's usually useful for free moving objects. Okay. So first thing you do is locate the plane of motion. In our case, it's the plane of this paper. So that's the plane of motion. Then locate the path and the point of interest. So the path is here. The point of interest is maybe one point is here, another point is there. So mark unit vector at point of interest along the path. That is called ET. So I'm going to mark the unit vector ET. And then I'm going to go here, mark the unit vector ET. I'm going to mark it in the direction in which the vehicle is going. Don't mark it in the other way. Okay. Mark the unit vector EN perpendicular to ET. So first thing is it has to be perpendicular to ET. It has to be pointing into the path in the plane of motion. What do I mean by pointing into the path is that it should be pointing into the curvature, into this thing. That's called EN. And here you can see that is called EN. Okay, that's called the tangent direction and normal direction. Coordinate ST is distance along the path. So if I start here, up to here is S1, and then I start here, all the way down up to here is S2. So that's the distance. Very nice. Speed is very easy. It's ds dt. How easy can you be? Right? Just like your high school physics. Velocity vector is speed times ET. And acceleration vector is rate of change of speed in this direction and speed squared over radius. So d dt of speed here, and this one will be speed squared over radius of curve. That's all you have to do. You got position, velocity, acceleration, and then we are off to applying Newton's laws. This is a very easy thing. I want you to understand that. Okay, so that's the whole idea. I've shown you step by step how to set it up. How do you strategize for use? When you're trying to do free moving particles, your first choice will be path coordinates. That is, if you know the motion, there's nothing like it. It's the easiest one. It's the easiest to use compared to straight line motion. Physically very intuitive. You have rate of change of speed along the path and speed squared over radius perpendicular to the path. This is the easiest thing. And all your high school formulae work very well for quantities along the path for constant tangential acceleration. So all your old formulae, you know, s equal to ut plus half at squared, v squared equal to u squared plus 2as work as long as you're looking only at the tangent. Don't worry about the normal component of the acceleration. They won't show up in any of these formulae. Okay, but otherwise, if your tangent component of the acceleration is constant, you can do exactly like what you did for your high school physics class. That is the beauty of this. Okay, the next kind of coordinate system we are going to look at is polar coordinates. When is it useful? When the path is not known precisely. If you look at this thing, you're spinning this thing, right? You don't know exactly where it will be, how fast it's going, you know, whether it's going to go up or down, all kinds of things are there. So we don't really know. So that's the time to use this thing, to use this coordinate. And the object, as long as you know that the object is kind of going around and around, periodic motion, then you should be able to do it. So if you spin this, depending upon what happens, it might be spiraling around this somehow. So that's a useful thing to know. And the input motion must be rotational. That's another point where you can use it. Okay. The way we do this one is to use our normal approach and write down the position vector and differentiate. Then use some clever notation. That sounds weird. I'll show you what I mean. So we're going to first do position and velocity. Oops. So here is my object. Right? Now, let's see. Yeah, so let's do this first. First thing to do is find the axis of rotation. That's that axis. Because you can see the rotation is around that. So that's called the z-axis. That's the first thing to do. The second thing to do is the plane of motion should be the plane perpendicular to z, which contains the center of mass of the object. The center of mass of the object is here. You will be tempted to put the plane of motion like that. That is incorrect. It has to be perpendicular to z through the axis. So it has to be this thing. That's the plane of motion. You're with me? This is very, very important. So please pay attention. The plane of motion is not decided by this one. It's decided by this. This is the plane. And then mark the xy axis in the plane. So this is the x axis, y axis going inside. Okay. Then the r coordinate is the distance from the x axis to the center of mass. So it is from here to here. That distance is r, not this guy. Please pay attention to that. It is very important to do these two steps. Then this direction is called ER. This direction is K. And E theta is going to be inside the board. That's called E theta. Okay. Theta coordinate, if I look at it from above, it's going around in some kind of a circle. So here is the axis of rotation. Here is ER. E theta will be like this. And the angle theta, if this is the x axis, y axis, angle theta is this guy. Okay, and E theta is perpendicular to these two things. Okay, so now we got the basic idea. Now we are going to figure out what's the position and velocity vectors. So position vector. So what I do is I'm going to mark it like that. So if I look at it from above, let's say here's where it looks like. Here is the x direction. Here is the y direction. Z is coming out. Here is the particle. This is r. This is theta. This is ER. This is E theta. Okay. And by the way, the I and j directions, I is like that, j is like that. So first thing we do is position vector equals, this length is r times r cos theta, r sin theta. So r cos theta I plus r sin theta j. Sorry, r is already counted. Well, once you get the position vector, it's pretty easy. So in general, both r equal to r of t, theta equal to theta of t, 2 degree of freedom system. In some cases it will be 1 DOF, but in this case we're looking at a 2 degree of freedom system. Both r and theta are functions of time. So now I'm going to do dr dt. And by the way, I'm going to write this as r dot. This is Newton's idea of putting a dot to mention d dt. So we're going to do that. I'm going to differentiate it by chain rule, and I'll get, sorry, product rule, and I'll get r dot times cos theta I plus sin theta j plus r times minus sin theta I plus cos theta j theta dot. This is just chain rule. So chain rule plus product rule. By the way, this vector has magnitude 1, and that is ER. And notice, if I take the dot product of these two things, I will get 0, cos theta I plus sin theta j, and minus sin theta I plus cos theta j. If you take dot product, you will get 0. So this is perpendicular to it, and that's E theta. So this vector is E theta. So mathematically speaking, instead of going on writing cos theta I plus sin theta j and all these things, we just use the short notation ER and E theta. Physically speaking, ER points this way, E theta points that way. Okay, so now we got position vector. So this I'm going to write it as r dot er plus r theta dot e theta. This is very convenient. By the way, there's one more very important thing. Er is cos theta I plus sin theta j. So er dot will be equal to minus sin theta I plus cos theta j theta dot, which is equal to theta dot e theta. Can you see that? Because e theta is that minus sin theta I plus cos theta j. Then similarly, e theta is minus sin theta I plus cos theta j, which implies e theta dot, again just use chain rule, will give you minus cos theta I minus sin theta j theta dot, which turns out to be minus theta dot er. Very nice, right? If I differentiate er, I will get theta dot times e theta, and if I differentiate e theta, I will get minus theta dot times er. Why is it useful? Because it will make my life in the second derivative much simpler. What do I mean? Let us go up here, and I got our velocity is now r dot er plus r theta dot e theta. And remember, er dot was cos theta I, was theta dot e theta, and e theta dot was minus theta dot er. This is just comes from differentiating cos theta and sin theta. There is nothing much to it. So now you differentiate again. dv dt is acceleration vector, which is chain rule plus product rule, r double dot er plus r dot er dot plus r dot theta dot e theta plus r theta double dot e theta plus r theta dot e theta dot. Just blindly use chain rule, blindly use product rule. Now substitute these two into this, and you will get r double dot er plus, now what is er dot? Er dot was theta dot e theta. You will get r dot theta dot e theta, that's this guy, plus r dot theta dot e theta, that's that guy, plus r theta double dot e theta, that's that guy, plus r theta dot minus theta dot er. That's this bit. Group the terms, and you will get r double dot minus r theta dot squared er plus 2 times r times 2 r dot theta dot, these two terms, plus these two terms, plus r theta double dot e theta. So that's how it goes. So you can see that position vector is r times cos theta I plus sin theta j. That's what everything starts. This is r er, and then velocity is r dot er plus r theta dot e theta. Acceleration is r double dot minus r theta dot squared er plus 2 r dot theta dot plus r theta double dot e theta. So in polar coordinates you have to do more differentiation. You will get a more messy formula for velocity acceleration, velocity and acceleration, but nevertheless, because you don't have to differentiate this every time, you can use this as a canned formula. It is more complicated than path coordinates, so this should not be your first choice. This should be your second choice. If nothing works, then you may have to go for Cartesian coordinates and do very messy things. Okay, thank you very much.